Before we insert, remove, or access any node or edge, we need to verify that these elements actually belong to the current graph. This step ensures that the structure remains consistent and that no invalid references are introduced. In most graph implementations, this check is handled by validate methods. These methods act as gatekeepers. They prevent operations on vertices or edges that do not belong to the graph. For example, in the diagram shown, the vertices labeled 0, 1, 2, and 3 form the actual graph. However, the vertex labeled 10 does not belong to it. If we try to perform an operation using vertex 10, the validate method would detect it, and then it would block the action. This will prevent the graph from being misused or corrupted. Start writing the validation methods. And before we do that, we will have to implement graphs interface to our adjacency matrix graph. So implements the graph interface that we made, this one, and then you will see the red lines is saying that we haven't implemented all of the methods in our interface. We just implement them, get all these methods. Okay. Now we have all of them implemented. By default, they will return these values. Okay, so now that it's done, we will have to, oh wait, before we do that, we will put these up so it's much clearer. Much better now. Okay, now let's write the validation methods. There will be private methods. Private inner vertex validate vertex. Okay, first we will check if the inputted vertex is null or not. If it's null, we can do nothing with it. So we'll just illegal argument exception and saying vertex cannot be null. Next, what we're gonna do is we're gonna check if this vertex is an instance of our inner vertex. We're gonna check if it's whether it's an instance of an inner vertex or not. If it's not an instance of inner vertex, then we will have to throw another illegal argument exception. And we will put in the error message as not a valid vertex for this graph. Next, we will create inner vertex. Inner vertex. We will do simple typecasting for the inner vertex. Okay. It's fine. And then we will check if we already have this inner vertex in our vertices list. So we still haven't done the attributes for the adjacency matrix graph, so we'll have to write them. So here we're gonna start writing attributes for the adjacency matrix graph. Okay, so the attributes start here. Oh, and also here are the current errors that we're facing. It's because we didn't put these things, the generics. I don't know why, but the automatic completion didn't put my generics. So we'll have to put it for each and every of these. This is very tedious. After fixing them, we will start writing the attributes for the adjacency matrix graph and then the constructor, and then we will continue on with the validation methods for both the vertex and the edge. Okay, so now we're done fixing them. Let's write the attributes. First, it will be a Boolean value for to check if the graph is directed or not. We'll name it is directed. Next will be the adjacency matrix itself. It will be a two-dimensional array of edges. Next, we're gonna have linked list, two linked lists, one for vertices and the other for edges. Okay. Next, we have an integer variable or attribute for maximum vertices, and another for vertex count. It will keep count of how much or how many vertices that our graph currently has. Okay, so let's move on to our constructor. Oh, we forgot to implement this one. Okay, now it's fixed. So let's write the constructor adjacency matrix graph. Make sure it's public. Boolean is directed integer capacity. Here we go, and we will assign is directed to this dot. Okay, and then maximum vertices will be this dot maximum vertices will equal to capacity. Okay, now we got the adjacency matrix graph, and then vertices will be a new linked list. Same goes for the edges, new linked list. Vertex count will be 0. Okay, so now we're done with the constructor and the attributes. So we will move on and complete our validate method. So now that our inner vertex is created, we will have to check if this vertex that we're giving in exists in our adjacency matrix graph. So we'll have to simply check if it is contained in our vertices linked list. So if vertices dot contains our inner vertex. If it doesn't contain our inner vertex, we'll have to throw another illegal argument exception. Given vertex does not exist in the current graph. Then we're done. We can just return the inner vertex. Okay, so what is it saying? Well, it's saying this. Inner vertex. Return. It was a typo. Okay. Let's move on to validating edges. So it will return an inner edge. Validate edge. Edge. Simple stuff, straightforward. If the edge cannot be null, edge cannot be null. And if the edge is not an instance of inner edge, if it's not an instance of inner edge, we will simply throw an illegal argument exception saying this edge not a valid edge for this graph. Okay. Then we will create inner edge. Typecast the edge, and then here are the extra steps. We have to gain the endpoints. That will be vertex v, vertex array endpoints, inner edge dot get endpoints. Okay, so here we will get the endpoints. So if the endpoints are null, we will have to throw argument exception, because an edge cannot have no endpoints at all. Turn the error uh, endpoints are null. Next, we will have to do the extra step, which is validating each and every endpoint that this edge has. So we need a simple for loop, vertex v, vertex in endpoints. Okay, so for each vertex v, we'll validate these vertices. And if this goes through, meaning that all the vertices that are the endpoints of this edge also exist in our current graph. It means both the vertices, I mean the edges and the vertices, as well as the edge exist in the graph. So it means it is a valid edge of the graph. We will return inner edge. Now we're done. So that we have finished writing the validation methods, next we will go on and implement each and every method and operation that our adjacency matrix graph has.